Hallo, hallo, hallo. Ja, wunderbar. Hi. Yeah, I saw that the preparation was in German, so I switched to English because I think most of the people understand better here in the room. Yeah. So I will take you a bit on a journey with air and water as refrigerant. Before we start this nice journey, I would like to introduce you shortly our company. So we are an engineering office sitting in Germany, doing sustainable refrigeration. So basically, we do product development in different fields like lyophilization, plasma freezing, and many other things. I will also hold later a presentation about heat recovery. So stay tuned. Yeah. So the journey I want to go with you. We have wonderful refrigerants available in the world. Yeah. Water and air are two of them I really like a lot and we use a lot. And before we start this journey, I want to share you this picture. I personally did this picture last winter in Germany. So what you see on this picture, let me see if I have a pointer here. So you see water evaporating cooling. What is it? Cooling towers in English. Yeah. So this customer in total has 50 megawatts installed cooling capacity on their cooling towers. In this moment, I took the picture. You see in the back, there's snow on the ground. Yeah, so we have outside temperature of -5 degrees. Yeah, and we are evaporating water to generate 6-degree cold water. Okay. So in the moment I took the photo, it's around 15 megawatts is running. And the other part of the story is next to it is a hospital. So with -5 outside ambient temperature, I assume the hospital could use some heat. And I really want to show this to you. In German, I always say in German it was very common back in the past of my grandfather that they were smoking when the kids were playing in the room. Yeah, so they were sitting on the sofa smoking. Yeah, if you would do this nowadays and tell your friends, I hope we're there in 20 years if we see something like that. Okay. Good. Let's start. So. This will be a bit fun journey. So if you want to have the scientific part, I will do later the presentation. Yeah. So we have a lot of customers in pharmaceutical industry and chemical industry. And in Germany, we have 80 million living people in the country and the same amount of heat pump experts. So we like to start a bit of beer. Yeah. So in Germany, we like to drink beer. This is beer from my hometown. And basically, if you have a warm beer in summertime and you put it into your refrigerator, basically the refrigerator takes the energy from the beer. And we call it beer energy. Okay? Keep this in mind. This is the most important takeaway of this whole presentation, beer energy. Okay? And basically, this wonderful machine takes power and brings this beer energy to a high temperature level where we can heat the kitchen. Okay? And the fantastic thing about a heat pump is that the beer energy is bigger than the electric power. Okay? And that's the beauty of a heat pump. Okay? And this ratio, so space heating, electric beer energy, this ratio is this coefficient of performance. Crazy, yeah? So basically on a good heat pump, we have around 4 or 5. That means with 1 kilowatt hour of electrical power, we get 4 to 5 electrical to heat. Yeah, it's just that we're all on the same expert level than the other 80 million in Germany, okay? Good, and what's state of the art? This is the brewery that produced this nice beer in my hometown, yeah? And they're not special, everybody does the same way. So they have a wonderful dry cooler, not a wet cooler in this case, but a wonderful dry cooler you see here in the picture, yeah? And I know it pretty well, it's with glycol. So they have a refrigeration machine that brings the heat into a glycol, and this goes to the roof. And this machine, obviously in summertime when there's 40 degrees on the roof, can bring the heat to the ambient. And next to it is a wonderful office building with 300 people working there, and they burn gas that they don't freeze in the winter time. Okay, smoking, yeah? So basically that's the ground idea, okay? Why should I talk about water and air in this context? These are two refrigerants that are on the far high temperature, on the far low temperature, which I will show you. So water is a fantastic refrigerant. It has 0 GVP, it has 0 ODP, it's not toxic, non-flammable, crazy. Yeah. What can you do with this water? I'm out of chemical industry, so I know water compression since many years. Yeah. Basically, what you do with water compression is usually in a big pharmaceutical plant like BASF in Ludwigshafen. It's huge. It's several kilometers long. They have usually one main place they produce steam, but crazy, they also need the steam on the other end of the factory. So they have compressors that they use to recompress the steam to have the same quality of the steam at the under end of the factory. Yeah. So this technology is available. It's installed since 30 years. It's many thousands compressors of this are already installed, working, and you can use, crazy idea, as a heat pump. So this is one process. I have to be a bit careful what I tell you, but this is a real process of a customer of us. He does basically sterilization, yeah, in this vessel here. So, I think here. So he's cooking something, okay? And he's cooking it, and he's getting boiled water over the roof on a level of 100 degrees because we are on ambient pressure, okay? And this boiled water, so this steam, he has to cool again because he's getting it as a water treatment. It's very bad things in this steam, okay? And today he's burning a lot of gas, so 20 megawatts of gas, to heat this vessel. And you can do beautiful things with it. So basically, if you take out the beer energy out of the stream that you have to cool anyway, yeah, and recompress this into the steam he needs, you can save up to 50 to 70% of his total gas consumption. What is a lot on 20 megawatts? So, and the good news is, COP don't get blended by COP. So this guy, 150 degrees, COP of 5, he's nuts. No, I'm not, because COP is always a delta. So our heat source is 100 degrees. We go on 150 degrees. It's not crazy, yeah? So this is always, you have to see on COP, always the heat sink to heat source. And that we do systematic in pinch. That's the other presentation. Okay, we were not involved in this wonderful project, but you can contact Harald Eros from Takeda. They're building this. Okay, so basically what they have today is already, even with brine, but here's is only cold water, they have installed in Vienna at Takeda a cold refrigeration machine with already a heat pump to 70 degrees. And this, so next year they are already installing a heat pump for high temperature. And then from the high temperature heat, they exactly use these compressors I just explained you for the steam production. And they do 184 degree steam with the waste heat of the refrigeration machine. Beautiful project. We are not involved, but we do similar things. Okay. The other refrigerant I want to share with you, how much time? Oh, I'm good in time. Wonderful. Is air. Yeah. Air is refrigerant, also very crazy. Who of you did not fly in his life? So you already experienced all air refrigeration. Each passenger plane in the world is air conditioned by air, so also nothing crazy. You have experience with it. It's used in the plane, and forget about air conditioning, other things for air refrigeration. I don't have it in the presentation, but usually air refrigeration is interesting below minus 40. We will see in a second, maybe. I don't know which slide's coming. But anyway, for air flying, also the transport rate of the refrigeration machine and also the high pressure on the turbine has a big impact. So for airplanes it's efficient, but also for ultra-low temperature. So I did not mention. So air had no GVP, no ODP, is not toxic, not flammable. Good. How is it working? We make an experiment, okay? We take a bicycle pump for your bicycle and we compress. You see the pump here, and we have a very strong thumb, so we close the pump. We compress, we have high temperature, high pressure, and then we wait some time and we equalize to ambient, so we have ambient temperature, high pressure. Usually you would have now a liquid, and you could like boil the liquid on the pressure, you need the temperature. That's not working with air because we have no liquid. So what we do, we let the system do work. It's a different kind of process. So we let the pressure get out the piston, and therefore we remove energy from the system, okay? And this energy we recover in the next compression. That's the whole magic. So this is how it works in every passenger plane in the world. So next cocktail party, you can talk smart about flying with air refrigeration, okay? If we want to do ultra low temperature, it's just imagine a second pump, okay? This pump we already prepared, like on the cooking, so it's already at ambient temperature. We cool it with the first pump. So say, make it easy, 20 degrees ambient, we reduced on 10 degrees with the first expansion. And now we pre-cooled to 10 degrees with the first pump. The second pump, we do expansion 0 degrees. So imagine a third pump, we had -10 and so on and so on and so on. So with very low pressure, you can go to very low temperatures. So how is it really working? We use this wonderful machine from Mirai Intex. It's produced in Czech Republic. It's a turbo compressor with a turbo expander on one shaft, and the motor is in the middle. So basically, it's a flying machine, speed controlled. It has no liquid refrigerant. It has no oil. It has no vibration. Those of you that know about refrigeration, the main failures of refrigeration equipment is liquid refrigerant, is oil, and is vibration. Pretty cool, isn't it? So what we do is we have a storage room, say at -80. The machine is an open cycle, so you already bathing in the refrigerant. Also a nice experience. Do this with ammonia or something else. So we suck the air from the room, compress it, and we have the high temperature, high pressure. Our high pressure on an open cycle machine is 1 bar overpressure. So also from a safety risk, this is a crazy machine. We cool it with cold water, 612 for example. Then we would have 20 degrees here, 1 bar overpressure. We go into the recuperator that I promise you will understand in a second. We are here -75. We expand from 1 bar overpressure to ambient pressure. We are -100. The -80 room heats up our -100 air to -80. We suck back the -80 air. We go into recuperator. We said we are +20, -80, same mass flow, gives here +15, and we go back into recompression. One rotating equipment, simple cycle. But the beauty of this is the turbo expander. That's why it's now and not 30 years ago. This machine can, the smallest turns with 86,000 RPM, flying on an air bearing. I like it. And also, to give you a bit idea, I have to look on the clock. Yeah, still good. To give you an idea, we can do many things completely different in refrigeration. We don't have to do always the same things. I can tell you about many other projects, but here, for example, we don't have an evaporator. I told you the room air is already the refrigerant, so we don't have the delta T over the evaporator, would also boost a lot our efficiency. And then you ask, but there are ice crystals and on -80 also CO2 crystals, and we have dirt and other things. Yes, and the machine is sucking over 2 filter cartridges. They are obviously redundant, so if one fails, it can suck over the other. And if they are full, they see it over differential pressure. They give a pressure shot against the flow. Yeah, it can still suck here. It gives a pressure shot, and all the dirt and nasty things are driven in the chain drive, and the chain drives mechanically removes out of the cold room, so you don't have defrost cycles and other things, so you can run all day long, same temperature, and go also more close to the critical temperature. I have another slide I expected. But anyway, so this is how it works, yeah. I brought you one of our projects that you see what is possible with air refrigeration. So for Revolution, we brought already over 100 machines into the field of air refrigeration. To give you a number, this is one process where we got the environmental impact prize of the German, Agency for Environment, yeah. Sorry, it's maybe not the best translation, but basically what's the process? They have this steel parts that they want to make super hard for trucks, for example, that they run 30 years. Yeah, they have to cool it down to -90 and then reheat to +400. And we, as I said, had got an impact price that we are so smart to make it 70% more efficient. How did it work? Basically, the first idea we had was that we said, okay, guys, you have an oven. The oven has a mass. if you always cool your mass of the oven minus 90, reheat plus 400, then cool down minus 90, reheat 400, this costs you a lot of energy. And we measured it with one customer that paid 180,000 euro a year, only with everything count out, only to reheat his oven. Yeah. So we said it's a bad idea to do two ovens. Total rocket science. Yeah. So we already saved a lot of energy. Yeah. The second thing we did not use liquid nitrogen. We used air refrigeration to give you a feeling. The Carnot process you see in the other presentation is a quadratic function. So the lower the temperature, the higher effort to generate it. So liquid nitrogen is minus 196 degrees. So a COP of 0.125 is realistic with transport and other things. If you do minus 90 with air refrigeration, maybe you have 0.4. Yeah. So you're already some numbers away. Yeah, at least 3 times. So this is also more efficient. And the other thing is, I make it quick, is that usually our customers, they get a truck full of steel. So they have 40 tons of truck, but you don't build an oven for 40 tons. You build an oven for 1 ton or 2 ton. Yeah. So we have different batches. Yeah. And we did 2 doors. So we basically said, you bring in the first batch, cool it down minus 90, leave it in the oven, open the other door. That's why we have these green lights. Open the other door, put in the warm batch, and then the refrigeration machine does nothing. We just recover the energy with the fan. They equalize. So the plus 400 oven doesn't start at minus 90. It starts at minus 40. And also our minus 90 oven doesn't start at plus 20. It starts at minus 40. Crazy. So 70% more efficient. We got a price, everybody happy. Okay, so basically that's possible if you think a bit more out of the box and do things a bit different. So at the end, I would just want to be aware, there's a lot of legislations that also help to make this innovative solutions into the market. Yeah. So basically F-gas regulation, sorry, it's in German, but F-gas regulation, I guess you're all familiar with it. It got enforced this year. That helps us a lot. Yeah. We have the PFAS draft. Careful, it's a draft, but it can hit hard. I mean, asbestos and other things disappeared thanks to the ECHA. So we are quite confident that it have the same, destiny for refrigerants. And we have in Germany already the energy efficiency law since November last year. So you're forced to not smoke with your kids, and you're forced to recover your heat from your waste heat. Yeah. And this is from a European directive. So I guess most of you that at least live in Europe will hit this law also, because Germany is first there, but the other will come too. So thank you for your attention. If you want to have the more scientific presentation, it will be in 20 minutes, I think in hall 4. Thank you very much.